In this module of Wave, we are going to learn about traffic signals, phasing, and timing. We are, by the end of this lecture, you will be able to define and explain key traffic signal terminology, like what is a signal cycle, what is phasing, you will differentiate between different signal operation types and also left-turn treatments, like what is a pre-timed signal, what is an actuated signal. You will be able to interpret typical signal head configurations and their implications. You will be able to apply formulas for yellow and all red intervals. You will be able to compute critical flow ratios and determine appropriate cycle length, and then use that to allocate green time to different movements within an intersection. And you will be able to develop a basic signal timing plan based on everything that you learned in the previous steps. With that being said, why intersection is important, why we are specifically talking about control of intersections, because intersections are the most complicated, complex location within transportation network. And the reason is because of the number of conflict points. So if we consider that there are three possible movements, turning right, going through, and turning left, from each approach of a four-leg intersection, and considering pedestrian activity as well, so we can face several conflict points that it may be manageable without any intervention of traffic engineers, or maybe we require some interventions. What does that mean? It means that we mainly have three levels of intersection control. Level one, that is something we call basic rules of the road. It means that I, as a traffic engineer, as a designer, do not get involved. It is the drivers who have the opportunity, the freedom, and the ability to make the decision at intersections. This is usually very local streets, low speeds, low volumes. If there is enough visibility of the conflicting movements, drivers are able to make a decision by themselves. Uh, Level two would be yield or stop signs. If we find out that rules of the road are not enough, that the drivers cannot make a safe decision based on the conditions, existing conditions, then we may apply yield, or if yield is not enough, stop signs, maybe on two approaches or maybe all four approaches. All approaches will be controlled by stop signs. And the ultimate control, ultimate way to control intersections would be traffic signals. Uh, how do we make that decision? As I said, based on driver's ability to avoid conflicts. See, potential conflicts is the most important visibility. So if we look at those first two levels, level one and level two, visibility of the a potential conflict is the most important thing. So we usually create site triangles and see whether it is adequate to come to a complete stop. And also traffic volumes and speed and things like that. Level one and level two outside the scope of our work here. We'll only focus on level three, which is traffic signals. Traffic signals, again, if we go back to the main themes in traffic engineering, which are safety and efficiency, they work on both of them. So they are going to provide an efficient movement. Imagine you have two arterioles that they carry high volumes. It would be impossible to control the intersection of those two arterioles without any traffic signals. Just it would be a deadlock at that intersection. People won't be able to negotiate right of way. So we will make the movement efficient by periodically providing cycles of right of way. And we also make it safe by making sure that we avoid the possibility of certain type of crashes at intersections. Signalized intersections must be warranted. So you saw that we have three levels. So we only go to level three if there is a need for that. Manual on Uniform Traffic Control Devices, MUTCD, has clear guideline on the warrants related to implementation and installation of traffic signals. Outside the scope of our work, I just want you to know that there is such information provided. There are two main important concepts when it comes to traffic signals. One is phasing, the other one is timing. Phasing shows the pattern or the order in which the movement happens. Timing is how much time each movement, each lane group would have to cross the intersection, to clear the intersection. And these are the two things we are going to learn in the lecture today. I will show you how we should design phasing. Most importantly, how we should decide about number of phases. And I will also show you how we can allocate, how should we decide about the duration of time that is assigned to each one of these different phases. Let's talk about a few terms that you will hear from me throughout the lecture today and make sure that we are all on the same page about them. The first one is cycle. That is one complete rotation through all of the indications. Remember, we have three indications on a traffic signal, red, yellow, and green. So a complete rotation of all these indications through the intersection, one complete, would be a traffic cycle. So, for example, imagine you arrive at an intersection and signal immediately turns to red. If I start my stopwatch and count the seconds until the next time that this same approach gets red, that would be one complete rotation, one cycle length. Time to complete one full cycle. We will learn in the lecture today how we can calculate an adequate cycle length. We have intervals, periods of time during which no signal indication changes. We have green, change, clearance, and red intervals. Green and red are clear. We know about them as a driver. You've experienced them every time you are crossing an intersection. Same thing for yellow. There is another interval, kind of a hidden feature of traffic signals called all red. What is all red? I'll talk about it in the lecture today as well. Keep it in mind. We'll get back to this. And phase is a set of intervals. There are other names for it. Some textbooks, some resources say timing stages, but I prefer to use the word phase. Also, traffic signals may come with different types of operations. One type is what we call it pre-timed signals. What is the meaning of a pre-timed signal? It means that everything is predefined. The cycle, number of phases, the way that the signal rotates, everything is predetermined. It does not vary by the demand that exists at the intersection. We may just have different plans for off-peak hours or weekend versus weekdays, but everything is pre-planned. If we have some sort of detection in place that we will assign right of way or we will assign the duration of green based on the demand that exists at an intersection, we have other types of operations, namely semi-actuated, fully actuated, and demand responsive. So all these three are based on the detection at the intersection. It means that we detect whether there is a demand on one approach. If there's no demand, we don't need to give them the green time, right? These pre-time signals, these are the ones that you are staying at an intersection and signal is green is red for you and green for the other approach, and there's no vehicle on the other approach, and you're going crazy. Why I don't get the green? Because you are not detected. It doesn't matter if you're there or not. Everything is predetermined. That is what we call pre-time signals. But if we have some sort of detection in place, we either have semi-actuated, fully actuated, or demand responsive. Semi-actuated means that we only detect vehicles on a minor approach. So imagine we have a major street, a big street, more number of lanes intersecting a minor street. Now, green by default is given to that major street. But if there is a vehicle on the minor street, now that would be the time to give right of way to those vehicles to cross the intersections. Versus fully actuated, that is if we have two major streets, two arterials. Let's think of two streets with three lanes on each direction or intersecting each other. Huge volumes, high speeds. It would be impossible to have no detection in place, or it would be just semi-actuated because these two are in the same class. So we have detections on all different parts. And then demand responsive, that is looking into the entire network, providing the most optimum solution for the network. By detection, the most important detection that we have, the most common, not the most important, that the right term would be the most common detection that we have in place is what we call in pavement loop detectors. So we put these wires in the pavement and they create a magnetic field. Whenever a vehicle crosses this magnetic field, disrupts this magnetic field, a call is sent to the traffic controller. So we know that there is a vehicle there. That would be the most common type of detectors, loop detectors. You should have seen that. Pay attention next time that you're driving. Pay attention to these wires that are placed in the pavement next to the intersections. It means that there is a detection in place. Now, if these wires are only on two streets, that would be semi-actuated. If we have them on all four legs of an intersection, fully actuated. But is this the only way that we detect vehicles? No, there are other ways, like we have cameras, radars, acoustic, pressure plates, push buttons. Each one of them serve a different purpose. Like for acoustic, first of all, cameras and radars, they are usually used for larger distances, longer distances. If you have a vintage point and you can look at the traffic from further away and make decisions based on what you see, you can use cameras or radars. We have acoustics, like they are the best for um, uh, in case of wrong way traffic, because the sound profile, if you're getting close to a point or if you're getting further away from a point, the sound profile would change. So based on that, we can make a decision. We can detect vehicles. Pressure plates and push buttons, these are mostly used for pedestrians to detect the pedestrians and then give the right of way and give enough time to pedestrians. So push buttons, usually you push the button and it sends a call uh, that there is a pedestrian here and we need to give them the crossing opportunity. Push pressure plates are usually placed in the pavement, these tactile plates that as soon as you step on them, the pressure is applied and it sends a call to the traffic controller. There are other types of detection in place, like we have emergency vehicle preemption, Opticom. You might have seen this at some intersections, most of the traffic lights. This device is mainly to detect if there are emergency vehicles approaching a signalized intersection. It either works with the lights or with the sound. So those infrared lights that are received from the emergency vehicles like an ambulance or a fire truck, they will let the controller know that an emergency vehicle is coming that way. So they will break the phasing scheme and they will assign the right of way immediately to the direction with an emergency vehicle. Uh, when we want to talk about phasing, the pattern in which vehicles move at an intersection, the most important question is what to do with the left turns. How we want to deal with the left turns decides a number of phases. And with that, there are three ways that we can treat left turns. The first one is what we call permitted, second one protected, and third one compound. So what is that? Permitted left turn is when you are turning left, but there is a conflicting through movement coming your way, and you have to actually yield the right of way to that through movement and find a gap to turn left. This is called a permitted or permissive left turn. We also have protected left turn, which means that we will stop the through moving vehicles, and then we will assign the right of way only to the left turning vehicle so they can turn left without any opposing flow at the intersection. We also have another form that is called protected permitted. For example, for the first few seconds of a phase, you can make the left turn protected. And then after that, you will, so if there's any vehicle waiting there, they can turn left, they can clear the lane. But after that, if someone arrives at the intersection and they want to turn left, they should look for an opportunity. They should look for a gap. If there is a gap, they can turn. Otherwise, they have to wait until the next cycle that will start with a protected left turn phase. We call this compound phasing. Um, Next one that I want to talk about here is configurations of traffic signals. We usually have these vertical signal phases, but in case we do not have enough vertical clearance, we may make the arrangement horizontal. Although this is not an ideal situation, the ideal situation is using the vertical alignments. If we have protected movements, whether it is protected left turn or protected right turn, we show them by arrows. And the way that those arrows are presented can tell us different treatments that are applied at an intersection. Like a solid green arrow shows a protected left turn. A flashing yellow arrow shows a permitted left turn. Also, a circular, so let's say, for example, this is a circular green for the left turn movement. A circular green is equivalent to a flashing yellow arrow. Both of them are representing a permitted left turn. And remember that with the permitted left turn, we are making the left turn amid the conflicting vehicles getting into the intersection. We also have the same thing for protected permitted right turns. It is less frequent compared to left turn treatments. At specific locations, if we have a lot of conflicts between right turning vehicles and pedestrians, so the pedestrians would be now the main conflict point, we may consider protected permitted right turn, which is going to use the same configuration, just arrows would be toward the right side. With that being said, based on the decision that we make about the left turns, we can make a phasing plan. Remember, I told you that there are two main things that we need to achieve with the traffic signals. One, what is the phasing plan? Two, what is the timing plan? So with the phasing, as I said, if a left turn needs to be protected, it means that we need to add an additional phase. Permitted, it means that we do not need an additional phase. How to make that decision? Next slide, I'll show you how we make that decision, whether to make a left turn permitted or protected. But before doing that, let's say that we make a decision whether it is protected or permitted. Now, how does the phasing look like? Let's go over a few examples. First of all, you see that some arrows here, they are dashed and some arrows are solid. There is a meaning behind that. If a movement is shown by a solid arrow, it means that it is a protected movement. If an arrow is shown with a dash in a dashed format, it means that it is permitted. So with that being said, in this first example, in this two phases scenario, let's say north is going up like this. Now we have a two-phase traffic signal. In the first phase, Everyone moving on the eastbound and westbound is released at the same time. Their through movements, their right turns, and their left turns. Then we stop east and west. We go to the next one that is south and north. Everyone is moving at the same time. You can probably guess which type of intersections would be using all, permitted movements. Probably low volumes, low speeds, no safety issues. These are the things that we will talk about in the next slide when we are making a decision about left turn treatment. Look at these two scenarios. So here is a three-phase scenario. We have left turns that are protected. Let's say this is the southbound left turn. This is the northbound left turn. We had to protect them, so they happen first. Then we have through and right happening in the second phase. And in the third phase, everyone on east and west is moving. So this is permitted left turn. In this another example, we have split phasing, which means that this is similar to that first scenario. We do not have protected left turns in terms of protecting that from the creating that in a separate, assigning that to a separate phase, but we have protected left turns in terms of moving the through movement from the intersection. So you see that in this first scenario here, we have permitted right, permitted left, and then we have southbound start moving through right and left, northbound start moving through left and right. Now, why would we do this? Usually, if there is, for example, only one lane, let's say that north and southbound is a roadway, is a street with only one lane. So if it is only one lane, and if there is a vehicle that wants to turn left and they cannot find an opportunity, they will block that entire approach, right? Everyone else should stay behind them. So in that case, we will separate them, split them from each other to give opportunity to everyone to move in one direction. Another example would be if the intersection is too tight, too narrow, that the two left turns, if they happen at the same time, they will collide. That would be another reason to split, or this split phasing example. Look at this. This is the most typical, this fourth example here. This is the most typical phasing scenario at when we have two major intersections, two major streets intersecting with each other. So you see that the left turns are both protected. We start with the left turns on one of the directions. In this example, it's westbound and eastbound left turn. Then we have through and right happening. By the way, why all the rights are dashed? Because right happens in conflict with pedestrians. So because we have pedestrians who are moving during these phases, the right is not protected. It is permitted, as is the case for almost all of these scenarios. Then we go to the other direction, protected left turns, and then we have the through and right. Some other examples, like these are reflecting lane configurations. For example, if there is an exclusive left turn lane, we usually show that with a separate arrow here representing. So this represents a lane that is shared between through and right, and this is a lane that is exclusively assigned to the left turn. Now, let's talk about this left turn treatment and how we should make that decisions. There is no national standard when it comes to signal timing and phasing. Maybe it was important to mention that at the beginning that, we just have some suggestions. And these suggestions are from different places, different resources. One of the best and most comprehensive source here is Signal Timing Manual that provides a flowchart to make the decision to whether make the left turn protected or make it permitted or make it a compound phase. Now, how is that decision made? There are a few things that you have to check. One of them is crashes. So one decision is made based on the safety issues. Then the other one is sight distance. Again, going back to that safety issue. So if you answer yes or no, then there are some other tables to refer to, or you can just jump to a conclusion. Side restrictions, if they can be removed or not, how many left turn lanes exist, how many through lane exist, are there fewer than three left turning vehicles per cycle? So the volume of the left turns, 85th percentile speed. Speed is always a very important determinant when we're talking about different parts of traffic signal timing or phasing. How many through lanes on the opposing approach? What is the cross product of left turn and opposing volume? Left turn delay here, and the critical number of protected permitted left turn related crashes. So you see that there are mainly three things that are considered here: crashes, a crash history, uh, and side distances that is talking about the opportunity that is available to see speed, I should say four then, and also volumes. Most of the times, if you do not have crash history, if you do not have information about the delay, for example, at an intersection, people just depend on volumes. Volumes, left turn volumes are probably always are going to give you accurate estimate of what we need to do. So higher volumes, they require a protected left turns, lower volumes. So they need a permitted. I would say a rough number is 200 vehicles per hour. So if there are 200 or more vehicles per hour turning left from one lane, that lane needs to be protected. Otherwise, it can be a permitted left turn. When we make that decision about phasing, we will show that on what we call a ring and barrier diagram. This is an example of overlapping ring and barrier diagram. So you see here that we have two left turns, but for one of them, we had a longer time because there was a higher demand for that. So at some point, we went to through on the north and right turn on the northbound, but the left turn was still happening, mainly because of the demand. So we may have overlapping scenarios, or that would be if we have actuated signals specifically. If we have pre-timed signals, most of the times we are just going to end up with non-overlapping phases. We also have different ways of different notations of calling movements and numbering movements and phases. This is one of the most common ones. So we start with the major streets and we assign number 2 and number 6 to the through movements on the major streets. And then we go to 4 and 8 for the through on the minor streets. This minor street could be also a very big arterial, but just minor compared to the other one. Then we assign the left turns with 1 and 5 and 3 and 7, as you can see. And then we go to the right turning movements and also to pedestrian movements. So this is a very common way of numbering phases and movements. So now that we know about phasing, which we learned it is mainly decided based on what we want to do with the left turns. Next step is to find enough time for different movements at the intersection. So we are gonna look into vehicular needs first. We will find what would be duration of yellow, change interval, what would be duration of all red, or clearance interval. I'll talk about them. We will find what is the most critical movement at an intersection on each approach to an intersection. We'll determine, we'll calculate lost times, talk about the lost times. We'll determine cycle length. Here is desirable cycle length. We have different types of cycle length. I'll talk about two of them in a few minutes. And we'll allocate the green time to these competing movements at an intersection. Now, this was all about vehicular need. We should also check whether we have enough time for pedestrians to safely cross the intersection. With that being said, let's start with a change interval. Change interval is shown by a circular yellow. The indication is circular yellow, and as probably all of you know, it is to warn drivers that signal indication or right of way is about to change from circular green to circular red. In other words, right of way is about to be terminated for the drivers on that approach. There are different laws when we talk about yellow change interval. Specifically, different states, they either adopt a permissive yellow law or restrictive yellow law. What does that mean? Uh, by the way, this is a map that shows which states, if it is yellow, it's permissive law. If it is brown, it is a or red. This is a restricted law, restricted law. What does that mean? If you are in California, as an example of a state with permissive yellow law, if you cross the stop line and you enter the intersection and during yellow and signal turns to red, you are a legal movement. You are on a legal movement. You can cross the intersection safely. But if you're in Oregon, like as an example of a restricted yellow law, it means that if you are within the intersection and the light, the indication turns to red, you are an illegal movement. You're a red light runner. So again, the difference is where you are when signal turns to red. So if you enter the intersection during yellow, very end of yellow in California, and signal immediately turns to red, you're fine. You shouldn't receive any tickets. Same thing if it happens in Oregon, you will receive a red light running ticket. Now with that, how should we design duration of yellow? Again, there's no national standard. There are different suggestions. I'm going to talk about some of them. Uh, the most important thing is that it should give enough time for drivers such that if they are too close to intersection and they cannot stop, they will safely and conveniently cross the intersection. Or if they're too far away from the intersection, they can come to a complete stop in a safe and comfortable way. MUTCD, Manual on Uniform Traffic Control Devices, suggests the yellow duration of yellow to be 3 to 6 seconds. There is a rule of thumb that I like. It's only rule of thumb. Don't quote me on that, but I've heard it from some traffic engineers that the duration of yellow should be almost approximately 10% of speed limit. So if you are designing a traffic signal on a roadway with 45 miles per hour speed limit, yellow should be around 4.5 seconds. But if you want to be precise in your calculation, ITE, Institute of Transportation Engineers, in their handbook, they have traffic handbook, they have a recommendation for the duration of yellow. And this recommendation is, it has a simple concept. So as you can see, duration of yellow has two terms. The first one shows the reaction time. So if you are driving and signal changes from green to yellow, it takes some time for drivers to perceive that signal change and react to that. IT actually suggests that to be about 1 second on average. And then the second part of this equation is based on basic physics. How long does it take for a vehicle that is going with an initial speed of v to come to a complete stop, a secondary speed, a final speed of 0? So this would be based on the basic physics, depending on what would be the deceleration rate and if it is on a grade. So if you're going up hills, the grade is going to help you to come to complete a stop faster, sooner, right? So G in that case would be a positive sign. If you're going down grade, grade is working in opposite of what we expect to. So it will take longer for the vehicle to come to a complete stop. So in that case, G would be a negative value. IT again suggests this deceleration rate, something that would be acceptable, comfortable for drivers in an urban area. that to be 10 feet per squared second. Next, we have clearance interval or all-red. And this is something that maybe some of you might not be aware that it actually exists at intersections. So next time that you're driving and you're waiting behind a red light, pay attention to the rotations of traffic lights. There is usually something about 1 second that all the traffic signals are showing red. That is not an error in the system. That is actually a very important component of the system. Why it is an important component of the system? Remember that a few minutes ago, I talked about permissive yellow law. That, like in a state like California, if you enter the intersection at the very end of yellow, you're not and signal turns to red, and you are at the intersection, you're not a red light runner. You're fine. You're totally fine. Now, let's think about the safety implications. If you enter the intersection at the very end of yellow, or let's consider the worst case scenario, you are a red light runner. You enter the intersection, you just made a bad decision. I'm sure it has happened to all of you, that you are approaching a signalized intersection, signal turns to yellow, you don't know what to do. We call it dilemma zone. You don't know if you have enough time to stop or you have enough time to cross the intersection. So let's say you decide to cross and you happen to be a red light runner. If I release the traffic on the opposing direction immediately, it will increase the chance of a right angle crash. So what do? I will assign a 1 second, something like that. I'll show you the calculation for that. So I will assign an all red interval such that this vehicle that is a late runner vehicle or is a red light runner would either completely clear the intersection or would be at least within the intersection in front of the vehicles in the opposing direction. So you can see that there is a potential hazard in the intersection. There's a red light runner, right? So we will remove that possibility of a crash if there is a red light runner by introduction of this clearance interval and or all-red interval. So that is where the name comes from. We want to clear the intersection before the opposing vehicles get into the intersection. So as I said, again, there's no national standard for this. The rule of thumb, again, is something about 1 second. Different traffic engineers, sometimes based on engineering judgment, they have different ways to calculate all red. But ITE, again, Institute of Transportation Engineers, they have a recommendation that is very again it is based on physics. So they are saying that the duration of all red would be the time that it takes for the vehicle to go W plus L, the width of intersection plus one length of the vehicle to completely clear the intersection. The vehicle should go the intersection, the width of the intersection, and it should also clear one length of the vehicle divided by the speed. And for the vehicle, they consider 20 feet to be the vehicle length, to be a passenger car vehicle length. After we find out what should be the length of yellow and all red, now is the time to find cycle length, and based on that cycle length, allocate enough green time to different phases that are available at an intersection. How do we do it? We will start by finding the most critical flow at each phase. What is the most critical flow? Let's talk about it. Let's say that this is an intersection, a four-leg typical intersection with three phases. We have protected left turns on the westbound and eastbound, and then we have through and right on the eastbound and westbound, and then everything on north and south is permitted. It happens at the same time. why we made that decision. Look at the volumes. Just the volumes are telling how we ended up with this decision. But now for every phase, I want to figure out what is the most critical movement. Because if I have, let's say, this left turn is the more critical one compared to the other one. So if I have enough green time to accommodate this left turn, it means that automatically I also have enough green time to cover the other one, the other left turn. By the way, everything that I'm talking here about is pre-timed signals. So we are making all these calculations for from now on for all these green allocations and cycle length. This is based on a pre-timed signal. One way to find a critical movement is just to look at the volumes and say whichever movement has a higher volume, it would be the most intense movement. It is not wrong to do that. Like I can look at this is 300 and this is 250, so I can say that this 300 is more critical one. But sometimes it might be inaccurate. How? If the condition of the left turn here is significantly different with condition of left turn here, let's say these 250 left turns, it includes a lot of heavy vehicles that it has a lot of parking activities on the other side. Or maybe there is a bus stop actually, as soon as people turn left, there is a bus stop here that a lot of times it is occupying the movement, the left turn movement. And there are so many other things, like if there is a grade, if there is a work zone activity, construction happening in that place. So how do we consider the condition in which the movements are happening? This is by something that we call saturation flow rate, and we show it by S. So saturation flow rate considers the conditions in which the movements is happening. It is a hypothetical number. Basically, if we make 1 hour of green, let's say that this left turn has 1 hour of green, how many maximum vehicle we can accommodate at that during that specific, with considering that specific condition. We have adjusted saturation flow rates based on the prevailing conditions. So in order to find the most critical movement in a phase, what we do is that we divide the volume by the saturation flow rate. So we'll calculate the saturation flow rate based on the existing conditions, and we divide these two numbers, the volumes, by the saturation flow rate. If the saturation flow rate is exactly the same, it means the conditions are the same. So the one with a higher volume would be the more intense one. If the saturation flow rates are different, then V over S ratio may be different may result in different decisions to find the most intense movements. And then for every phase, we find the highest value of the V over S ratio. We call it flow ratios. And that would be used to calculate cycle length and also to allocate the green time, because we need to find enough time for the eastbound left turn such that then westbound left turn also is going to receive enough green time in a pre-timed non-overlap phasing. With that being said, there are different ways to calculate minimum cycle length. To calculate cycle length, we have minimum cycle length, optimum cycle length, desirable cycle length. There are theoretical equations here and there to find the cycle length. I want to talk about two of them in this lecture: minimum cycle length and desirable cycle length. So minimum cycle length will be calculated using this equation. L, which is the total loss times what is the intersection utilization divided by intersection utilization minus the summation of flow ratios. Let me very briefly talk about the variables here. Loss time. What is loss time? Every time that we stop traffic and we start moving that, some time is lost. Why? Imagine you're waiting in a line and signal turns green. It takes some times for the vehicles to perceive the signal turned green and to react to that and start moving and get to the intersection. So you see that some time is lost as soon as we start moving the traffic. We call it initial or startup lost time. Then assume that we want to stop the traffic. So signal turns to yellow and turns to all red. Not every vehicle is going to use the entire yellow and all red. So that duration is not going to be utilized every time that we have a rotation in traffic cycles, right? In intersection, in the signal cycles. So what happens is that part of that is also lost. We call it clearance lost time. Then we have a lost time per phase. That would be the summation of this startup lost time and clearance lost time. And if we find that for the entire cycle, for all the phases that are in one cycle, we will find L, which is the total lost time for every cycle. Then this is the capacity. This is what we call V over C, volume over capacity ratio, which means that for what percentage of capacity we are designing for. Are we designing for 100% of the capacity? Or do we want to design only for 80% of the intersection capacity? We call it intersection utilization. Depending on different conditions, different situations, it might go somewhere between 80% to 100%. And then we have flow ratios, sum of flow ratios that comes from the previous step, finding the critical flows and add them together. V over S ratios, and N is number of critical lane groups, uh, mainly whatever number of phases that you had. So this would be the minimum cycle length, which is this basically ignores the efficiency of the system. We are just trying to accommodate everyone within the intersection. But if we want to accommodate that in an optimum, in an efficient way, there are other ways like this is a Webster equation to find optimum cycle length, and the variables are as previously defined. We can use this to find desirable or optimum cycle length. When we find cycle length, next step would be to allocate the green time. So let's say that you have 90 seconds of cycle length. You have three phases. How long should be the green on each one of these three phases? The total, we know that green, yellow, all red, if we add this, one complete cycle duration is 90 seconds or 120 seconds or 60 seconds, whatever we got from the previous step. Now, how long should be the green for each one of the movements? There are multiple strategies, different strategies. There's again no national standard to find the duration of the green, but the suggestion that I found most useful and efficient is to distribute the green based on how we found the critical movement in every phase and a ratio that shows cycle that is based on cycle length and lane group V over C ratio. So as you can see here, first of all, this is lowercase g, that is what we call effective green. Effective green is the amount of time that is effectively used by drivers. So we have two things. We have capital G, which is the green time that is shown, shown on the display on the traffic face, the traffic signal. But we have effective green that is effectively used by drivers. So this effective green time is the green time plus yellow time plus all red time minus the lost time, the initial startup lost time and clearance lost time. So we can find that effective green by multiplying whatever was the V over S ratio for that phase multiplied by cycle length that we calculated previous step divided by utilization, lane utilization or V over C ratio for that lane group. There are different strategies, different textbooks, different resources. They have different ways of allocating green, even different engineers based on their experience. It's completely based on engineering judgment. They may make different decisions, but I found this one to provide fair timing for different phases. Now, everything up to here was about vehicular movement. The last thing to check is, okay, is there enough time for pedestrians to cross the intersection or not? Let's say that we have 20 seconds of green for vehicles, but if pedestrians want to cross, they need 30 seconds. Then that 20 second is not providing adequate time for a safe and efficient movement of pedestrians. Then I have to fix that 20 seconds. I have to increase it to 30 seconds. Although vehicles don't need it, pedestrians need it. So how should I find that duration of green for pedestrians? Again, no national standards. There are different suggestions. Uh, Sometimes engineers make their own judgments based on the conditions of the intersections and based on the profile of people, pedestrians at that location. But I found this to be one of the most effective ones of finding the duration of green for uh, pedestrians walking. What is that? It is based on the effective crosswalk width, whether it is more than 10 feet, 10 feet equal to 10 feet or more, or sorry, less than or equal to 10 feet or more than 10 feet. That is the width of the crosswalk, not the length. I'm talking about the width. And then duration of green would be based on the length that they should cross divided by the speed. So this is physics, right? How long, what is the distance that they should travel divided by the speed with which they are traveling, and number of pedestrians, the effect of having too many pedestrians or very few pedestrians on each other working in groups that will also impact the ability of pedestrians to move in that crossing. So if WE, that effective crosswalk, is 10 or less, we will find by this equation, or if it is more than 10 feet, another equation. Now you see that there is a constant part here, 3.2 seconds. What is that? This is something that we call startup pedestrians startup time. It includes the time for pedestrians to perceive that signal that they have the right of way now, they have the green light to cross, to react to that, and move from the place that they are standing until they get into the intersection. They step into the travel lane. On average, they found out that 3.2 would be a good number to be considered as a constant here, the length that they should cover, they should cross, and the impact of pedestrians moving with together. For the speed, there are different suggestions, but the most frequently used is 3.5 to 4, 3.5 or 4 feet per second. But if it is a specific intersection, my suggestion would be to conduct a speed study to make sure that, for example, it's an intersection in a place that is mostly resided by elderly. We should definitely consider the speed, the limitations walking in walking speed in that condition. And then we will compare this, as is written at the end, and as I mentioned a few minutes ago, we should compare this with the time that is given to the vehicular movement. If this is less than that time, we're fine. If it is more than the vehicular green, we have to fix the vehicular green such that it will give enough time to pedestrians to cross. This lecture used different resources, some two textbooks mainly, and two manuals. The manuals, Traffic Signal Timing Manual and Manual on Uniform Traffic Control Devices, both of them are available for free. You can download a PDF, and also some parts of the material came from these two textbooks.